Hello again, everybody. Welcome to our third video in our Systems of Linear Equations series. Today we're going to is part one of a two-part topic, and the topic is substitution method. Substitution method is one of the algebraic methods we're going to talk about. So the non-visual ways for finding the point of intersection. Before we get into the substitution method, I want to talk about a couple algebraic method basics. For the algebraic methods, we find a way to turn both two variable equations. These systems always have x's and y's in them, right? So those are two variables. And we turn them into one equation with only one variable. So we're going to find a way to turn these two equations into just one equation. And instead of having two types of variables, they're going to only have one type of variable. We can then solve this new equation to determine the value of the remaining variable. So if now we turn it into one equation and it only has x's in it, we can solve for that x, and then we can use that x to help us solve the y. So once we determine the value for one variable, we can go back to an original equation and determine the value of the other variable. Another thing I want to talk about before we get into the substitution method is this idea of equivalent equations. An equivalent equation is when you adjust an original equation so it contains different numbers. Equivalent equations represent the same line as before, but now it looks different. And it looks different in order to give you an advantage. So if we ever manipulate an equation, like you can see what I've done here, I have x plus y. If I was to times x plus y, I'll write it here, x plus y equals 1, and I multiplied this by 2 for some reason, I would get 2x plus 2y. That doesn't look very nice, but plus 2y equals 2, which I have to the right there. And if you look at their lines, they're the exact same line. So we're going to be making some equivalent equations. I don't want you to think that we're bringing in new lines. We're actually representing the same two lines the entire question. It's just we have different ways to represent them, and these different ways present new opportunities. So we might get stuck one way with one presentation. We can change the look of it, and it's going to open up some possibilities for us. It's going to allow us to do some other things. And again, don't worry, it's still the same two lines. All right, enough talk, right? Let's actually get into solving this. So I'm going to number these two equations. So I'm going to use two different colors. Why I number, if you can't remember, or maybe I forgot to mention it in a previous video, it's just for organization. You do not need to. So that is something I like to do. You don't have to do it. Another thing I like to do, I might as well talk about right away, is I draw these dotted lines sometimes. It's just to break up my work. I'm like a lot of you out there, I don't like wasting my paper. So I don't like leaving large spaces of unused paper. To avoid that, I draw my little dotted line so I know that the work isn't continuous and it doesn't necessarily have anything to do with each other, and then I can kind of save some space. So you'll see me drawing these kind of page breaks just to break up my work. Okay, so the first equation. Oh, sorry. I was getting into solving already. Substitution method. What we do for substitution method. Okay, in substitution method, it's actually exactly what it sounds like. You guys are used to, with equations, substituting values in. So what I mean is if I told you x is equal to 2, and you had an equation 2x plus 4 equals, I don't know, let's say 8. Sorry, I kind of blanked there. You're used to taking that value and substituting it in for this variable, 2 times 2. Now, so we took this here and we replaced the x with a 2 and y because we had that statement telling us x was equal to 2. We're doing that exact thing today. It's just we're not going to always have a variable equal to a number. That'll happen sometimes. We're going to have a variable or a term equal to some other variables or terms. But otherwise it's the same idea. So back to our question now. What we want to do is we want to try to search for a term to isolate in order to sub it into one of the two equations. So what do I mean by that? If we look at this, this would be a term, this is a term, this is a term, this is a term. These are all my potential targets that I'm going to choose one of these and isolate them. Now, whenever you have a lone variable, like just that x sitting there, that is the best thing to isolate. So you don't really know why I'm asking you to do this yet, but I'm going to ask you to isolate that x in the x plus 2i equals 2. As we do it, after you've seen one of them, it'll make a lot more sense the second time. So in my second equation, I'm just going to write out x plus 2y equals 2. And I want to isolate x, so I'm going to move this 2y away. So x equals 2 minus 2y. If you chose to write it negative 2y plus 2, that would have been fine as well. Okay, so I've reorganized this. So now what I'm going to start doing is when I reorganize things, I'm going to give them a new number. Why? Just so you know that when instead of always referring to it as the x equals 2 minus 2y, I can just say equation 3. And again, this is an example of an equivalent equation. So I'm representing the same line, but now it just looks like a different set of numbers. Okay, so if I've got x equals 2 minus 2y. So just like I had x equals 2 up here and I replaced the x with a 2, I'm going to now go into the other equation, this equation 1 right up here, and I'm going to replace the x that is in it with the new statement 2 minus 2y. So, page break here, I'm going to sub equation 3 into equation 1. So, what I just did there, that is just me writing a little note down to myself. I like to do that. Again, you do not need to do that. I think it has some benefits though. It just helps me track my thinking. It also keeps me focused. And if something interrupts me, it's easy for me to pick back up in my work because I've left little notes for myself. Substitution method has a few steps to it. So it's a longer process, meaning there is chance that you might lose focus at some point. It's nice to have these little notes down. Okay, so I will write down my equation again. So equation 1, it's going to be 3, maybe I'll write it in blue actually, 3, and I'll highlight my x in red, however, plus 4y equals negative 4. So where that x is, it's going to be replaced with the 2 minus 2y. So 3 bracket plus 4y equals negative 4. And just like I brought the 2 in my little opening example, the x equals 2 example, I'm now going to replace the x with 2 minus 2y, and that comes from up here again. So that's the big step in this process. Once I've done that, you can see I've gotten rid of the x's and now I have y's only. So I've taken my two equations, I've combined them into one equation, and I've cut down from two types of variables to one type of variable. Now what I can do is solve it just like it's any linear equation, any one variable equation. You would have done these types of questions in your grade 9 maths. So get rid of my brackets through distribution. 6 minus 6y plus 4y equals negative 4. Carry my work up here. Collect my like terms. So I'm going to have 6 minus 2y equals negative 4. And I'm trying to isolate that y, so subtract my 6. Negative 2y equals negative 10. Divide by negative 2, divide by negative 2. Y equals 5. So what that means is for the point of intersection, because remember the point of intersection is the solution, we know the y coordinate is 5. All right, now what do I do? So now what I do is substitution method again, except now I'm just going to substitute y equals 5 into one of these original equations. So I just worked with equation 1, so now I'll work with equation 2. So I will sub y equals 5 into equation 2. I just worked with equation 1, remember, so that's why I chose equation 2. And again, that little note I wrote down is optional. So x plus 2, that's where y will be. I'm being kind of lazy. I want to keep my colors. There we go. X plus 2y equals 2. So then x plus 2, open bracket, where I'm going to substitute that value in. And then this is where that 5 goes in. And now I just solve, and again, you can see that I've managed to get rid of one of the variables, so now I only have an x, so I just solve for that x. X plus 10 equals 2. Oops, minus 10, minus 10. X equals negative 8. So now I think I have my answer. I have my point, negative 8 and 5. What we can do is we can check it. we can simply check that solution. Negative 8 and 5. What would you do to check it? Well, you would just check it with the two equations you just worked with, or your two original equations. Remember though, we just solved for the second equation, so I know it works for that guy. Really, I only need to check it with the first equation. So 3x plus 4 times y equals negative 4. So this is negative 8 and this is 5. That's my solution that I'm plugging in. Negative 24 plus 20 equals negative 4, it says. Now I'll solve the left side. Left side results in negative 4. The right side already is negative 4. Means that is the correct answer. So the solution set for this, or my answer for this question, would be negative 8 and 5. Now, with regards to checking, totally optional. It's smart to do. So if you're in a test or a quiz situation, maybe solve them first, and if you have time, go back and check them, or check just the ones that you're kind of worried about. It's good to have confidence in your work, so I don't think you need to check every single thing, but you need to know how to check, so if you don't feel confident, you can check. Let's look at another one. Here are my two equations. Okay. Again, if you ever see a lone variable, that would be the thing to target. So I see this y right here. That is what I want to isolate, and then I will replace the y in the second equation with whatever expression I come up with. So for equation 1 here, 2x plus y equals 3. I'm going to subtract 2x, y equals negative 2x plus 3. That is my new equation, so I'll call that equation 3. Okay, so now let's sub this equation 3 into, well, again, just so you're not confused, I just worked with equation 1, so I'm going to have to work with the other equation. So equation 2. So I would get, for the equation 2, 4x plus 3y. Sorry, it slows me down to change colors like that, but I think the color coding helps. So then now where y is, I'm going to actually replace the y with this negative 2x plus 3. So 4x plus 3, open brackets, equal to 5. Now where that y was, here comes negative 2x plus 3. Okay, just like subbing in a number, now it's not a number, it's an expression. All right, once we got that in place, now we just have to solve. Again, we've turned the two equations into one, and we've cut down from two variables to one variable. So now I'm just going to solve for this x. So 4x, and then I have to distribute that, minus 6x plus 9 equals 5. Push my work up there. 4x minus 6x is negative 2x. Plus 9 equals 5. Subtract 9, subtract 9. Negative 2x equals negative 4. Divide by negative 2. X equals positive 2. Okay, so I got part of my solution. I know one coordinate out of my point of intersection. Now the second part is a lot quicker. So I will sub. Let's switch to blue, I guess. I will sub x equals 2 into whichever equation I choose to work with here now. So I just worked with equation 2, so now let's go back to equation 1. You don't want to ever sub something back into itself. So if you're wondering why I'm flip-flopping, so I wouldn't want to sub x equals 2 back into equation 2 because that's where I generated that answer from. So I should really work with the other equation where the answer did not come from. Although you could say that answer kind of came from both equations, I get, because I've combined them. But so equation 1, 2, and then that'll be my x plus y equals 3. So then 2 bracket plus y equals 3, and then I will replace the x with this 2, and then I'll just solve. So 4 plus y equals 3, subtract 4, y equals -1. Okay, so that's what we think our answer is. I can check it again. So I'm checking the point 2, -1, and I just worked with equation 1. That's where I generated that answer. So truly, when we check, I guess we should, I shouldn't say guess, I know, we should really check it with both equations. But seeing I kind of know it's going to work with 1 because I already plugged the 2 into that equation and it spit out the -1, so it's destined to work for equation 1. I really only need to check the second one, although I technically should check with both. And I'll show you, I'll check with both right now. Hopefully you're not groaning at home like, oh my god, man, just get done this question. These are a little bit longer, I do realize. So I'm just writing that out. So this would be 4 minus 1 equals 3. My left side works out to 3. The right side works out to 3. It worked for that guy. Second equation, 4 times x plus 3 times -1 equals 5. So that's 8. This is -3 equal to 5. Let's figure out the left side. That's 5. The right side already was 5. So it checked out there too. So you can see it worked for both. Like I was saying, I think that you're safe if you just check with this second one because all our answers came out of this first one already. We already knew the x worked with it because I plugged it in and it spit out that y. So yeah, that's what I would suggest there. So again, solution set to wrap this up. 2 and -1. One last example, and why I want to show you this example is what happens if you don't have just a plain old x or a plain old y lying around. And you can see in this one I don't. So I'm going to go ahead and just number these first of all, 1 and 2. When you don't have a plain old number, x or y, or an isolated variable already, what you have to do is you have to start looking at the variables. So I'm looking at the x's. And then I'm looking at the y's, and you want to see, well, are there any common multiples of each other? Like, can 12 and 4, is there any way I can kind of, do those numbers work together or anything like that? And 25 and 5, is there anything that, any way those numbers can work together? Or be made equivalent, I should say, by when I'm saying work together. Same with 12 and 4, is there any way I can make those equivalent, or the 25 and 5? Well, I'm going to focus on the x's. It would work in both cases here, the x's or the y's though. But what I can do is, if I think of 12x, I should go back to yellow here, I could rewrite 12x in terms of 4x. So I could rewrite 12x as 3 times 4x, right? And that still means 12x. And then what I could do is isolate the 4x in that equation too. And then whatever expression I come up with, replace it. For the other one, 25y. Well, I could rewrite 25y as 5 times 5y. That still means 25y, and then I could isolate for the 5y. So I'd have 2 possible ways to go. You only have to work with one way, or you only have to do it one way. So I just kind of work with the first thing I see, so I'll go with the x's method. So to rephrase what I was saying before is if you don't have an isolated variable, see if there isn't a connection between the variables in the 2 equations and see if you can rewrite the one term in terms of the other one, like I've just done. So let's get doing that. So I'm going to take equation 2, and I'm going to isolate my 4x. So 4x equals -5y minus 1. New arrangement, new number. Remember, it's the same line though. It's still line 2. Okay, and then what I'm going to do here is I'm going to sub that into my equation 1. So sub 3 into 1. 12x. I'm going to write 12x as 3 times 4x. So 3 times 4x, which means 12x still, plus 25y equals -13. And then now where 4x was, I'll put that expression I found. So now from here on, it's the exact same question. And again, where did I get this negative 5y minus 1? It was right from there. Once you've done that, now everything else is the same, so I have nothing new in the rest of this example. I just wanted to show you how to get around when you don't have a lone variable. I'll finish maybe my y off here, but I don't know if I'll go the whole way because I know this video is getting kind of long for you guys. And after that, I really don't have there's no real purpose to watch me solve the rest of this equation because nothing else is different. 10y minus 3 equals negative 13. Again, I'm just going to wrap up this to y. I'm going to write that out once. I'm sorry. Quit talking so I can go super fast, although I'm not going any faster, am I? But just to show you that it solves out the same way. The trick, though, again, is if you don't have that lone variable, you got to do what I just did in this one. I'd still have to solve for my x. I'd still check it and everything else, but everything from here forward moves on, just like the previous two examples. Okay, so we're going to stop here for now. I have to show you some fractions, but I do realize the video would be really, really long if I showed you 3 more examples, because these substitution method questions, they take a minute or two. So once you get the basics down, go to video 2 and check out I guess they're more complex, but they contain fractions. Have a great night, everybody.